Alright guys, we're going to get started with these 2D horizontal launch notes. And when we say 2D horizontal launch, we're just referring to a projectile that is launched from some height above the ground, and it only has an initial horizontal velocity. So for instance, right here I have a cannon. Okay, this cannon is located at some height above the ground. And we can see that this cannon is perfectly horizontal to the ground. So let's take a look at what would happen if we launched that projectile and there was no gravity. Well, if we launched a cannonball out of this cannon with no gravity, it would look something like this. The cannonball would leave the cannon right here, and then sometime later the cannonball would be right here, and then right here, so on and so forth. So we can see that if we launched our cannonball out of our cannon and there was no gravity to impact it, that cannonball wouldn't fall downward. It would just continue to move perfectly in a horizontal straight line. The other really important thing to note is that not only would this cannonball continue to move in a perfectly horizontal line, it would also move at the same velocity. So its velocity would remain the same because gravity is not pulling it down, and there's no other forces or anything else acting on it in that horizontal direction. We're going to assume, like with all of our problems, that air resistance is negligible and that we do not have any. So our cannonball is going to continue to move at the same velocity for the entire path while it's in the air. Now let's pretend that we turn gravity back on, and this time we just drop the cannonball. So initially we fired it horizontally, but now we're going to pretend that we just went up to the edge of the cliff and just dropped it off the cliff. So we know that our cannonball would be in the same spot right before we drop it, and then after we drop it, we know that it would fall a little bit, and then it would fall a little more after a little bit of time, and then it would continue to fall more and more and more until eventually it reaches the bottom of our cliff. So as you can see in the picture, the cannonball is moving faster and faster and faster. There's more distance between each of these cannonball drops as the cannon falls more and more and more, because gravity is accelerating that cannonball at a rate of negative 9.8 meters per second squared. Over here, I said that gravity accelerates it down at 9.8 meters per second squared. Down is telling me that it's negative, right? So remember, we can say direction with either a negative sign or a word like down. So when looking at a horizontally launched problem, we need to take into account both of these. We need to look at both the x and the y and how it plays a role in what the trajectory of our object is going to look like in that air. So if we do that really quick, we see that after a certain amount of time, if we're combining the x and the y, they're going to meet at these points. So by combining all of my points, I'm going to see that after a certain amount of time, my cannonball is here, then it's here, here, and now here. And if I, again, connect the dots here, I can see that the motion of my cannonball out of this cannon looks something like this. And that motion is just your basic trajectory, right? It looks almost like a half of a parabola here. And that's exactly what we would expect from an object that is launched horizontally in the air. We know that the horizontal velocity is not changing, but we do know that the vertical velocity is changing. As that object falls, it's moving faster and faster and faster due to gravity. So like we said, when we launch a projectile, both of these things are happening at the same time, and it's going to result in the ball traveling in an arched path, just like we drew above. Before we look at a problem, let's talk about some important pieces of information that are going to help us solve any type of problem in the future. So for instance, if I asked you, well, how long does it take this ball to reach the ground? When we have a 2D horizontally launched problem, the way we're going to solve this is by splitting up our x and our y components. So what that would look like is something like this. I would write my x, and then I would write my y, and I'd make it in kind of a table format here. I would list my variables just like I've had before: do, df, vo, vf, a, and t. And again, these are split up now. The reason that these are split is because the horizontal and the vertical components do not impact each other. So anything that's happening in the x direction is not playing a factor on anything in the y direction. Those two are completely separate. The only thing that they share, which is the same, will be the time that they take. So for instance, if I wanted to figure out how far did this cannonball move before it hit the ground in the x direction, well, that would be the same time for how far did the cannonball fall before it hit the ground in the y direction. So something important to note is that time is the same for both the x and y. Other general things that we can always say are the same when we have a horizontally launched projectile from some height will be the initial distance in the y. So again, remember to make sure that you're setting a good origin. So if we had a problem just like we had above with our cannon and we're launching our cannon from the top, down here is where I want to put my origin. So if I put my origin at the bottom, I point it up and then to the right, that means that my initial distance for my y is always just referring to my height. And that means that my final distance, if I'm asking for where it's going to be at the ground, is always 0 meters. So 0 meters, and then again, I'm just going to put in parentheses here when referring to the ground. Another really important piece of information is going to be our initial velocity in the y. The initial velocity in our y is always going to be 0 meters per second because it's only launched horizontally. Our final velocity? Well, our final velocity in the y is going to be unknown, most likely. We're not going to know that answer. And our acceleration, again, is always going to be negative 9.8 meters per second squared. And this is just because of gravity. So now that we got those key pieces out of the way, let's look at the x side too. And what are we always going to know about the x? Well, for starters, our distance initial in our x is always going to be 0 meters because we're always going to put our origin in a good spot. And that spot is going to be at the beginning of our path. Our final distance is going to be the total distance traveled in the x direction. So that one most likely will always be unknown. We're not going to know how far our object lands. Our initial velocity in the x will most likely be given to us. If not, though, we'll have to figure it out. Regardless, the initial velocity in the x will be equal to the final velocity in the x. So these two things will always be equal to each other when we have a horizontally launched projectile. The reason being is that our acceleration in the x direction is 0 meters per second squared. We are not accelerating the x direction, therefore we are not changing our velocity, so our initial and final velocities in the x direction are the same. Last thing I want to discuss is you might be asked to find out, well, what velocity does our cannonball hit the ground with? And let's say that, again, our cannonball is right here when it hits the ground, and it's asking for what is the velocity of that cannonball when it hits the ground. The key word here is that when I'm asking for the velocity of my cannonball, I'm talking about the total velocity. And the total velocity is referring to the combination of the x and the y velocity. Anytime we're looking for the total velocity, we're going to need to combine our x and y velocities. And the way we do that is by drawing our x velocity. So again, let's say that this is our velocity in the x direction. So we'll just name it Vx for some generalized velocity. And it's pointed to the right because my cannonball is firing out to the right. In the y direction, we know that it's pointed down because the y direction always points down and my object is falling downward. So like I said before, when combining vectors, we need to connect head to tail. So we're going to go from the head of our x direction velocity and put the tail of our y direction velocity right there. Now, to figure out what our total velocity is, we're just going to combine those. And like we said before, we need to take the resultant. And to do that, we're going to notice that we have a triangle. And we're going to notice that the resultant vector, or our total velocity, is just our hypotenuse. We're also going to notice, though, that this total velocity vector has some angle associated with it. Because like we said before, velocity is a vector, so it has to have magnitude and direction. So the easiest way to solve for our total velocity would just be to use Pythagorean Theorem, saying our total velocity is equal to, and I'm going to simplify it real quick, the square root of our velocity in our x direction plus the velocity in the y direction squared. Remember though that the velocity in the y direction is going to be negative, so make sure you're putting it in parentheses so it squares the negative, okay? If you don't put it in parentheses, you're going to have a mistake and you're going to get the wrong answer. This is going to give us the magnitude, and then to figure out the angle associated with it, we just need to take some trig function. I recommend just doing inverse tangent. I think if you go with inverse tangent, you can't go wrong. And by doing inverse tangent, we get tan inverse of opposite over adjacent, which would be our Vy over Vx, is going to give us our angle. Remember to make sure that your calculator is in degrees here. If you use radians, you're going to get the wrong answer. And your angle for a horizontally launched problem will always be a negative angle. The negative angle is in reference to our horizontal axes, and the negative is just telling us that we're moving clockwise from that axis. So we're going this way. If it was a positive angle, then we would be moving counterclockwise, and we would be moving this way.